Okay, so last time we saw the definition of uh, morphism of varieties. So, which is written right here. So, a map phi from x to y between varieties is said to be a morphism if you can cover x with open affine subset ui, and there exists an open cover vi of y such that phi of ui is contained in vi, and phi restricted to ui is a morphism of affine varieties. Okay. So this is equivalent to saying that uh, for each point P in X, there exists an affine open subset U of X containing P, and an affine open subset V of Y containing phi of P, such that phi restricted to U is a map from U to V, and it is a morphism of affine varieties. Yeah? So both of them are sort of equivalent. It's you can show it using basic topology. Yeah, nothing deep about it. So last time we discussed a few examples of morphisms of varieties. So the theme, underlying theme of those examples were that if you give a map between projective varieties, which are if you give a map between homogeneous coordinate rings of two projective varieties satisfying certain condition, then it defines a morphism of projective varieties in a contravariant way. So like in the affine case, yeah. So in the affine variety, but in affine case you get some sort of an equivalence of category. So it's not that strong here, but at least meaning every morphism between affine variety comes from a map between a ring homomorphism, K-algebra homomorphism between the coordinate rings. So there is a bijection. So here, I don't think you can't assert that, but in fact, the projective variety. So the homogeneous coordinate ring, they themselves depend upon the embedding. Yeah. So yeah, so maybe that is something I should have done before getting into more things. So maybe I'll do an example. Yeah. So so you consider P1. Yeah. So P1, the homogeneous coordinate ring is the homogeneous coordinate ring. Genius coordinate ring. One way of thinking about P1 is, or the standard way of thinking about P1 and its homogeneous coordinate ring is K x naught x1. If you think of P1 as in P1 itself, yeah. But you can also think of P1 as embedded in P2. So, so how do you think of P1 as embedded? So, yeah. So if you think of it as a line, then it's not going to be. Yeah. So yeah. So think of. Yeah, so maybe I'll come to this example. Yeah. So for that also, I'll have to talk about morphisms of varieties. Yeah. So you can embed P1 in P2 in many ways. Yeah. So one is, you know, you can think of P1 in P2 as, you know, A0, A1 going to A0, A1, and I don't know, you put something here, 0, for instance. Yeah. So this is so this is not good. So then if you do the calculate the homogeneous coordinate ring of P1 as subset of P2, where you are basically sending x2 to 0, then it's kx not x1 x2 modulo ideal of x2. So that is not interesting, but maybe you can do something like so this is one map, but you can also do another way is to give a map from P1 to P2 like this. So degree 2 map, yeah. So A0, A1 goes to um, so um, how do I want to write this? Um, yeah, so yeah. Yeah, so maybe so this should work. Yeah, so A0 square, A1 square, and A1 A2. Okay. So all degree 2 terms, if I put, yeah. So this, so note that if so first of all, this is a well-defined map. So if you replace A0 A1 by lambda times A0 lambda times A1, then this gives you the same point. But also, if I mean, and you want to make sure that uh, so if all three of them are 0, A0 square is 0, A1 square is 0, A1, A2 is 0, that tells you that, I mean, A0 square is 0, that means A0 is 0 and A1 is 0. So the target is indeed in P2. Yeah, you don't get 0, 0, 0, no matter which A0, A1 you choose in P1 and which point of P1. So this is well defined, and one can show that uh, it's an injective map, and we will argue that this is a yeah. So this guy. So the
The last term, should it be?
image
Hello, can
image
you
of
hear me?
phi
Hello.
is some subset of P2, and this is um, so if you want to write down, let's call it y. Yeah, so homogeneous coordinate ring of, so we can ask, I want to argue that Y is an algebraic subset of P2. In fact, I want to argue that Y is a subvariety of P2. And then we want to say that it's same as P1. Yeah, so it's somehow isomorphic to P1. So isomorphic, we will argue in a bit, but maybe at least it's an algebraic subset. So I of y is um, so I of y. So it is an algebraic subset. So maybe instead of calculating I of y, which is a bit more tedious, I'll say y is zero set of some polynomials. So let's say P2 homogeneous coordinate of P2 is given by x, maybe um, x, y, and z. So sorry, maybe homogeneous coordinate on P2 is given by x naught, x1, x2. Then this is zero set of um, um, yeah. So this is zero set of uh, x2 square is equal to x1 square plus x. Yeah, so this is zero set of x1 square plus x naught square plus x1 square minus x2 square. Yeah. So so you can check that if any element, triple which satisfies this uh, mm, will be of this kind. And of course, this satisfies any triple a0 square, a1 square, a1, a2 does satisfy this homogeneous polynomial, and conversely. Yeah. So this is the image is an algebraic set, and then one has to argue that y is so y we know is a projective variety. Yeah, it's a curve in P2, and then in fact we will show this is isomorphic to P1 in a bit. Okay, so I'll discuss this example. Um, yeah, so let me. In last class, we gave some examples using such formulas. So let me formalize this. Yeah. So I hope I'm recording. Yeah. So let X be a projective, X and Y be projective varieties embedded in Pn and Pm. And their homogeneous coordinate ring is given by, let's say, kx naught to xn mod I and ky naught to ym mod j. Yeah, so by the way, coming back to, so I didn't finish the argument here. So what is the homogeneous coordinate ring of y? So homogeneous coordinate ring of y ring of y is k k x naught x1 x2 modulo this ideal. Yeah, this is a prime ideal, so there is nothing else to do. X1 square minus x2 square. Okay, so I of y is also going to be this thing, ideal generated by this, since this is already a prime ideal. Yeah, so as you can see, so if you believe that P1 and Y are isomorphic, you can see that homogeneous coordinate rings are not isomorphic. Yeah, I mean, so Kx naught x1 is certainly not isomorphic uh, uh, to this ring. So for instance, yeah, so uh, yeah, so mm, so why are they not isomorphic? So the point is it has one bad point. So um, so yeah, so maybe is there a easier way to see this? Mm, so I'm just trying to figure out some property I can tell you which you're familiar with about rings, which one has and the other doesn't. So um, yeah, so I think UFD works. So you can show that. So this, of course, Kx naught x1 is UFD. I don't think this is a UFD. Okay. So yeah. So I think you look at x2. X2 you can show is irreducible, but ideal generated by x2. Yes, but x2 is ideal generated by x2 is not a prime ideal. So x2 you can show in this ring that x2 is irreducible but not prime. Okay. So that says that the two rings cannot be isomorphic. but they define, but they give rise to same projective variety. Okay.
Hello.
Okay, so let me get to this proposition. So let X and Y be two projective varieties. Let with homogeneous coordinate ring this and this. And suppose phi is a morphism, a ring, a graded ring. So whatever this graded means, so I'll just say what it means. So be a graded ring homomorphism. So it has to be a ring homomorphism. Phi should be a ring homomorphism such that phi y, such that phi yi for each I. So yi's are there. So phi yi or phi yi bar, let's say, is homogeneous of degree d. Yeah, so is homogeneous of degree d. Of homogeneous of degree d for all I between 1 and m, all I between 0 and m. So there exists d greater than 0. So d is some fixed positive integer such that each of phi yi is homogeneous of degree d. So remember, I and j are homogeneous ideals. So I in particular is a homogeneous ideal. So this is a graded ring in the sense we talked about last time. So you can think of it as phi yi is lie in dth component of this graded ring. Or another way is to think about it is phi yi bar is image of a homogeneous degree d homogeneous polynomial in x naught to xn mm, mm, uh, mod I. Yeah. So there exists a degree d homogeneous polynomial in x naught to xn such that its image in kx naught to xn mod I is same as phi of yi bar. So this is what graded ring homomorphism. This is what for us graded ring homomorphism is, and we want such that zero set of I mean, this we are thinking it in yeah. So now yeah. So maybe yeah. So if you so if you take those homogeneous polynomial in x naught to xn whose images are phi yi bars, and you consider the ideal generated by these and I, that should be empty. Okay. Then phi defines a morphism of projective varieties. Phi tilde, which will from x to y, which will send uh, points of x, we think of it as in terms of homogeneous coordinate. We are thinking of x in Pn. Yeah. So it's equivalence class of a naught to an, and we'll send that to phi y0 a naught to phi y0 evaluated at a naught to an, phi ym evaluated at a naught to n. Okay. So this is the set map we are given. Yeah. So remember, we have to show that this is a well-defined map between from x to y, and we have to show that is given by so the affine open subsets of x and affine open cover of x and y, such that when we restrict, then we get the morphism of affine varieties. Yeah? So to say that this proposition holds. Okay, so this is what we were doing here. Yeah, so here are, I mean, in the first example, are um, um, yeah. So what was so P1 to P2? So we and giving this map P1 to P2 was giving a map in the other direction in terms of homogeneous coordinate ring. So so there are m is 3 and n is 2 here. Yeah. So y0 will go to x0, y1 will go to x1, and y2 will go to 0. Okay, so that was the uh, yeah. So 0 is considered homogeneous of every degree. Yeah, so with the convention that so uh, maybe let's put it here. Convention 0 polynomial is homogeneous of every degree. Of every degree. Yeah, so okay, and in the second in B, y0 um, goes to x0. So the image of y0 is x0 square. Image of sorry. Um, Yeah, image of y0 is x0 square, image of y1 is x1 square, and image of y2 is x1, x0 x1. Okay, so there is some problem here. This should have been a1, a0, a1. A2 doesn't exist, yeah, a0, a1. Okay, so that is so if you want to translate this in terms of homogeneous coordinate ring, this is what is happening. Okay, so let's verify this. Yeah, so let's verify this proposition. So this is how we will give maps between projective varieties. So first note that phi tilde is indeed well defined. So since so we have to show that if we choose a different representative of this equivalence class A0 to AN, then we get the same answer. Yeah. So let's say lambda A0 to a different representative typically looks like lambda A0 to lambda AN for lambda not equal to 0 in K. For lambda in K cross phi yi lambda A0 to lambda AN is um, so by definition it is uh, so phi yi is a homogeneous polynomial of degree d. Yeah. So you will pull out a lambda power d and you get lambda power d times phi yi a0 to an. Okay. Yeah, so maybe the way to think about it is phi yi bar, I'll think of it as some homogeneous polynomial in x naught to xn, and then I put bar. Yeah, so maybe that is how we will think about it. Um, so maybe I should put here phi yi bar. So phi yi bars are in kx naught to xn, and if I put bar on phi, then it will be element of the ring kx naught to xn mod I. Okay, so they are in yeah. So this is okay. So we don't have to worry about. Um, So we get this, and hence we know that. So that tells us that phi y0 lambda times this vector is same as phi. So the equivalence class doesn't change because we just factor out. The two this phi yi lambda times a naught to lambda times an is just lambda power d times the previous guy. So the equivalence classes, so they define the same equivalence class in um, in so this is a map. So from Pn to Pn, yeah, x to y. So they define the same equivalence class. Okay, so phi tilde is well defined. Is this okay? That phi tilde is well defined? Yes, Aritra, you had some question?
Yeah,
Hello,
actually, that was hello.
Aritra?
Yeah,
Aritra? Um, yeah, you're not audible, but I thought I could hear everyone. 1 second. Yeah, try again. Maybe I missed. Aritra?
yeah, hello.
Yeah, now I can hear you. Sorry.
No, actually, that was for the map you said for the map you gave for P1 to P2. That
Yeah,
one.
yeah, tell me
So,
again.
so, so the last coordinate. Okay, so you corrected it later. Yeah,
Oh, okay.
you had
Yes.
written A1, A2. That's what I
Yeah,
was
I had
saying.
written A1, A2. Thanks. So I guess I missed it. Then when I went back, I realized it. Were there any other questions which I missed? Sorry about that. Somehow my um, laptop went on mute.
Okay. Yeah, it's
Any other questions so far? Oh, okay. Okay. So I guess I hope not. Yeah. If there are anything you can ask me. I'm sorry I wasn't able to hear. Okay. So so note that phi tilde is well defined since for uh, so we established that. Now we want to find open covers of y and x such that when we restrict it to those, then it becomes open affine covers. Then it becomes morphisms of affine varieties. Yeah. So for y, we will take vi to be y intersection yi not equal to 0. Yeah. So on Pm, our homogeneous coordinates are y0 to ym. Yeah. And on Pn, we will take the homogeneous coordinate as x naught to xn. That is the convention we have taken. Yeah. So we know that if we take vi to be y intersection yi not equal to 0, then vi is an open affine subset of y. Yeah. In fact, yi not equal to 0 is an open affine subset of Pm, and since y is a algebraic subset of is in fact ith affine cover of Pm. Affine. So yi not equal to 0 is isomorphic to Am, and it covers. So um, it is an affine space, and if we intersect y to this, we get an affine we get a closed subset which of that affine piece. Yeah. So vi is an affine open subset of y for I between 0 and m. So we get m affine open subset. And let's look at what happens to phi tilde inverse vi. Yeah. So what is phi tilde? Phi tilde was this map. So phi tilde inverse of vi is those points of x such that phi yi a naught to an is non-zero. Yeah, because we want an element of vi. Yeah, so vi uh, is y intersection yi. So of course, if a naught to an belongs to x, such that so we want the ith coordinate phi, so its image is by definition here, its image is phi y0 a naught to an, phi y1 a naught to n, and so on. And if we want it to lie in vi, we want the ith coordinate should be non-zero. Yeah. which is same as saying phi yi a naught to an should be non-zero. Yeah, so phi tilde inverse of vi is precisely these points. And these points we can write it as union of these sets. Yeah, so we'll take I equals 0 to n, a naught to an in x, such that phi yi a naught to n is non-zero and aj is also non-zero. Yeah. So we want both aj to be non-zero and this phi yi. So actually these should all be yi bars. Yeah. So okay. So so we want both phi. So this is a polynomial in this is a homogeneous polynomial in in n plus 1 variables. We want when we evaluate it on a0 to n, it should be non-zero and aj should be non-zero. And this is a union over j equals 0 to n. Okay. So of course, as we so since a0 to n is an element of Pn, one of them has to be non-zero. Yeah. So this union certainly covers the whole of phi tilde inverse vi, because one of the edges will be non-zero, and we declare this set to be uij's. Yeah, is to be uij. Okay, so first thing we will show is that uij is indeed an open subset of a fine open subset of x, and then we will so we'll give a map. Of course uij will cover. So uij, if we vary j, will cover vi. We'll cover. So we will show that uij covers whole of x, yeah, and then that's it. And then we'll give a map. So from ui, we'll get a map from uij to vi as j varies. So and we'll show uij's are affine, and that's it. So when we restrict phi tilde to uij, we'll show it's a morphism of affine varieties. So note that what is uij? So, so we want aj to be non-zero. Yeah, so that means it lies in uj, where uj, remember, okay, so where uj is given by xj not equal to 0 in Pn. Yeah, so this was the standard affine space, affine open subset of P and jth affine open subset of P. Yeah? So you consider x intersection uj. So since we are saying aj is not zero, any element in uij has to be contained in x intersection uj. And secondly, we also want that this should be non-zero. Phi yi bar a0 to an should be non-zero. Yeah. So we have to remove the zero locus of this guy. Yeah. So zero locus of phi yi bar a0 to yeah. So maybe one can yeah. So this guy is affine. Yeah. So this guy is already affine. This is affine open in X. This we know. Yeah. And now I'll remove a zero locus of a so affine open in X, and it's a, so you can also think of it as X intersection uj is a closed subset of an. Yeah, both ways we can think. And if we remove this closed subset, which is given by so if aj is not non-zero, we can divide by aj and the point doesn't change. Yeah. So what I'm trying to do is I'm trying to dehomogenize phi yi bar. to get a regular function on coordinate ring of x intersection uj. Yeah. So note that phi yi bar, which is a homogeneous polynomial in n plus 1 variable. If you think of it as so if you think of it as x0, x1, xi, xj minus 1, 1, xj plus 1 to xn, this becomes a polynomial in n variables instead of n plus 1 variables and not homogeneous. So this becomes a polynomial in the coordinate ring of uj. Yeah. So this belongs to kuj, coordinate ring of uj, which remember is precisely so here is kx naught to um, kx naught to xn, but you have to remove this guy. So maybe I'll write it here. So this is equal to k x naught, you remove xi and xj, sorry, and xn. So it's in n variables. And remember here xi is capital Xi. So with is capital Xi over x capital Xi over capital Xj. Okay. So what I'm trying to say is that we have taken so this is a x intersection uj is a closed subset of an, and we are removing a closed subset of closed subset of another closed subset of an from it. So what we get is an open subset in x. Yeah. So uij is open, and again since we are basically if you we are inverting this image of this in the coordinate ring of x. Yeah. So this is so maybe I can just write what the coordinate ring of uij is. So uh, coordinate ring of uij is going to be k uh, uh, x naught over. So if I give you the coordinate ring, that completes the proof of that it is an affine. Okay, yeah. So maybe this is how it is. And so in terms of xj hat xn, but you have to, since you are looking at so you have to intersect that. So maybe yeah. So and maybe I can just invert first and then go mod. Yeah. So 1 over this polynomial phi yi bar um, evaluated at phi yi bar evaluated at x naught to xn with xj removed, and then you go mod the dehomogenization of the ideal of x. Yeah. So um, which I denoted by I. Yeah, ideal of x was I. So IA. So IA is remember the dehomogenization of I, but with respect to xj. Yeah. So given a polynomial f in a homogeneous polynomial f in I, you just in x0, capital X0 to capital Xn, you plug in small x0 for capital X0 and small xn for capital Xn, and at the jth coordinate you plug in 1. So this is what the coordinate ring of Uij is. So Uij is indeed an affine open subset of X. Yeah, and it covers and it obviously covers X because UJs cover the whole of Pn, and union of UJ covers the whole of Pn, so it covers X, and each of these um, yes, and um, um, yeah. And and the image lies in some vi. Yeah, so image of any point in X lies in some vi, so it will lie in the corresponding Uij. Yeah, so that is how you can show that Uij's cover X. And so, okay, so not so maybe. So I should have detailed it much more, maybe not union of Uij as j runs from 0 to n is phi tilde inverse of vi. Okay, and if you put I equals 0 to 0 to m, then you put union I equals 0 to m, and that becomes X. Okay, because these phi tildes are phi tilde inverse. So this is not phi inverse, but phi tilde inverse. Phi tilde inverse of vi. Okay. So that's how you can show that union of Uij's cover whole of X. And now if you think about it, what is phi tilde restricted to Uij? So it sends a point a0 to an to this point. Yeah, so this was the map. This is the map here, right? So but this point is same as since on Uij Aj is non-zero, you can divide by Aj. Yeah, so these 2 points are same, and on Vi the ith coordinate is so on Vi we are taking Yi is non-zero. Yeah, so the ith coordinate is non-zero, so we could divide phi Yi by this guy. So this is but remember this point is same as um, a0 to an yn. Yeah. So note that this point and this point are same, because phi y is 0 if you whether you evaluate it at a0 to I mean you can take so we know that if we evaluate it at this point as we use this representative or this representative, it doesn't matter. And secondly, we can always divide by phi yi. Yeah, and this is indeed so note that these are phi y, so phi y0 is a homogeneous polynomial, but if we when we plug in x0 to x0 to xi minus xi minus 1, 1, xi plus 1, xn. This is a regular function on on ui on uij. In fact, it's a regular function on x intersection uj. Yeah. So all the numerators here are regular function, and denominators are also regular functions on uij. Plus, we know that the denominators never vanish. So phi yi evaluated at a0 to an is not equal to 0 on vi. Yeah, so we are on uij. Yeah, so this is a function on uij because uij is a subset of phi tilde inverse of vi. Yeah, so and vi we are taking to be so phi tilde inverse of vi is those where phi of yi bar a0 to an is non-zero. So this is non-zero for all on uij. So that tells us that this though this is since we are taking a we are taking fractions. This is a priori a rational map. Uh, uh, so in these rational maps, so the rational maps. So these are elements of the coordinate ring, and we are taking the ratios. So these rational maps are regular. The rational maps maybe phi y0 bar over phi yi bar are regular on uij's. So that tells you that these phi tilde uij restricted to uij is defined by regular functions. Yeah, and hence phi tilde restricted to uij is a morphism of affine varieties. Yeah, so it's just homogenization and dehomogenization. Maybe I said more words than I should have, but hopefully it's not too confusing. So I hope this makes sense. Yeah, are there any questions? Maybe if you ask some questions, it may help you clarify what I'm trying to do. Okay, so if so, I guess I've said enough about this thing. So let's get to this example. So this is the example. So this was y. Yeah. So let's call this. I've called it C here everywhere. But anyway, let's stick to what we did. Maybe let's call it C itself. Or let's call it y. It will be consistent. Yeah. So we know that this is a phi is a morphism because it's defined by, so we are using some homogeneous coordinates here. Yeah. So y is a subset of p2, And the definition is what we are going to do is send A0, A1, A2 to A0, A1. So, okay, so is, first of all, is phi a morphism? So we have to check. So of course we are defining it by homogeneous coordinate, but we also should check whether this is well defined or not. Yeah. So maybe both A0 and A1 is 0. Then what happens? Then this is not a point in P1. Yeah. So what if A0 is 0 and A1 is 0? What happens? And then A2 has to be 1. So, so is that a problem? So what I'm saying is 0, 0 under this map. If you think of it, this map from P2 to P1, yeah, y is contained in P2, and we are thinking of a map from P2 to P1. Then of course 0, 0, 1 doesn't go anywhere. Yeah, but what happens to this point 0, 0, 1? So this will be a problem only if 0, 0, 1 lies on y. Yeah. Otherwise, all the other points have an image. Only 0, 0, 1 doesn't have an image. Yeah. So, so does it lie on y 0, 0, 1?
No, it doesn't.
It doesn't. Yeah. So we just check it. We plug in a0 x0 equals 0, x1 equals 0, and x2 equals 1. Then it doesn't satisfy this equation. Yeah. So this is well defined on y. If you try to extend it to p2, it's not defined. But on y we are still good. Yeah. So on P2, this is not, this is what you can say is a rational function, rational map. Meaning is defined on an open subset of P2 away from, in fact, 0, 0, 1. But on, since that point doesn't lie on y, we are still good. Yeah. So phi does define a morphism. But so let's ask our question is this. So we know that. So I told you to believe me that this is indeed P1. So first of all, is phi an isomorphism? Will phi will this phi work as an isomorphism? So to check something is an isomorphism, it has to be first of all bijective. Yeah. So once you have a bijection, then I mean it's you're almost there. Yeah. So let's just check whether phi is a bijection. Yeah. So let's take some point of P1. So I don't know. Uh, Phi inverse of let's calculate some point. Yeah. So maybe 1, 0. 1, 0, a0 equals 1 and a1 equals 0. Yeah. So what is phi inverse of 1, 0? So we want a0 to be 1 and a1 has to be 0. So we are looking at a0, a1, a2 such that a1 has to be so maybe we just put in those values which we know. So a0 has to be 1, a1 has to be 0, and a2 which satisfies this equation. Yeah, such that a2 a0 square is 1. So 1 square plus 0 square minus a2 square should be 0. So 1 minus a2 square should be 0. Yeah. So there are two possibilities for a2. Yeah. So this set is precisely this set is precisely 1, 0, 1 and 1, 0, minus 1. So these 2 points of P2 are on Y as well, and they both map to P1. Okay. So that tells you that so that in particular tells you it's not a bijection. Yeah. So it can't be an isomorphism. Okay. So maybe we'll try to change things a bit, yeah, and try to, but there is an isomorphism from between this and P1, yeah. So what we can do is we will change um, we'll take an automorphism of P2, yeah. So if I do a linear change of variable, yeah, so if I declare y0 to be x0, y1 to be x1 minus x2, y2 to be x1 plus x2, then this gives me a map from P2 to P2, and of course we can recover x1 x0 x1 x2 from y0 y1 y2, because for instance, x1 is just y1 plus y2 over 2, and x2 is just y1 y2 minus y1 over 2. Yeah. So and so this is an isomorphism of P2 to itself, and so we are just trying to change coordinates on P2 and think of y in this new coordinate. Yeah, so if we think of y in this new coordinate, then we have x naught square is same as x1 square, x naught square plus x1 square minus x2 square. This in terms of yi's become x naught square is just y naught square, and x1 square minus x2 square is same as x1 minus x2 times x1 plus x2, which is same as y1 times y2. Yeah. So this and this y uh, becomes zero set of this guy in new coordinates, in new homogeneous coordinates. Y0, y1, y2. Yeah. Okay. And now if we consider, yeah, so in this setup, I think maybe, yeah, so what map, so the point is, I see yeah, so I don't know if this one will work, and since we have limited time, I'll try to take some shortcut. So the point is, um, if we consider so I want to look at some affine piece of it so that it becomes a parabola. So we know that parabola and line are isomorphic, so that is what I'm trying to do. Yeah. So you consider y1 non-zero. Yeah. So y1 equals 1. Then in this so you divide by y1, so to speak. Then this becomes y0 square minus y2. Yeah. Y0, little y0 is y0 over y1, and little y2 is y2 over y1. Okay. So this will plus y1, yeah, not minus y1. It doesn't matter. Okay. So the map should be somehow yeah. So this is this so zero locus of this guy is so z of this is in A2, and if we project onto so another way to say is that coordinate ring of OY intersection y1 not equal to 0 is k y naught y2 mod y naught square plus y2. But this, of course, is isomorphic to is actually equal to ky2. Yeah, because y naught square is just minus y. Y is ky naught, sorry, not y2, but ky naught, because y2 is just minus y naught square. Yeah, so there's so that is how, so this is isomorphic to ky naught. Yeah, so the map should be projection onto y naught. Okay, so the map um, from y to p1 should be projection onto y naught. So it should be uh, uh, y naught y. So a naught, a1, a2 should go to um, a naught and um, projection onto y naught. So and I'm dividing by, so it should go uh, and so you divide by a1, so a naught over a1. So anyway, zero. Yeah, sorry. So I want to send a naught over. So I want to send a naught over a1, 1, a2 over a1 to a naught over a1. Uh, um, um, and 1, let's say. Yeah. So that is uh, yeah. So I think maybe the map is of so from y to p1, we think of the map as uh, so something is so. Yeah, so A2 is just determined from A2 over A1 is just determined from A naught over A1. A2 is just square of A naught over A1. Yeah, so this is okay. So we sent A0, A1. So I'm just trying to extend this map. Goes to A0, A1. Okay, so you consider this map from y to p1 given by this guy, yeah, in terms of these new coordinates. So so of course, if both a0 and a1 is 0, that means both y1 and y2 are 0. Then uh, if both y1 and y2 are 0, a capital Y1 and capital Y2, then y naught has to be 0 as well to be on y. Yeah, so this map uh, phi phi2, let's say, is well defined. Map of projective varieties. Okay. And then you have to check it's an isomorphism. Okay, so the way we have cooked up away from a1 equal to 0, so if a1 is not equal to 0, then it is an isomorphism. So that is how we cooked up. Yeah, and when a1 is 0, then you can check that so if a1 is 0, that tells you that so what is the equation? A1 is 0, so so y1 is 0. So y naught has to be 0. So they and then so if a1 is 0, then a naught has to be 0. This implies a naught has to be 0. And hence a2 has to be something non-zero, and you can take it to be 1. So then the only point in y which has for which a1 is 0 is 0 0 1. I hence so this corresponds to the point 0 0 1, and this sorry, something went wrong. if A1 is 0, then oh no. So this map is not well defined. Sorry. Yeah. So this is
So confused by this because these kinds of maps are just projections, right? Projections from a point on P2 to some one-dimensional line, right? In P2. But your variety is to as
yeah.
so generically the map you expect it. Right? So why can't you cook up a isomorphic?
No, but P1 is, I mean, Y is indeed isomorphic to P1. Yeah. It's just that.
Yeah, but it's a degree 2 copy of P1 inside Y. So if you project, generically you should expect the projection to not be an
Right. So
isomorphic.
if I do the projection, this won't work. Yeah. So I have to do something
It
else.
will never work, right? Yeah.
Yeah. So this is not right. But this is the map which we want to extend. Yeah. So the map. Yeah. So 1 second. So sorry, I should have worked this out earlier. So I thought. But the map at the affine level is this thing, and this is what we want to sort of extend. Okay, so actually we have a map in we have this map P1 to yeah. So yeah, so I guess we should use this map. Yeah, so we have a map from P1 to P2, and why is that? So we should give a map from P2 to P1 so that we get something like this. Yeah, so to get the inverse. Yeah, so let's see. So I'm trying to give you. Yeah. Yeah, so maybe it is not easy. So basically, one may have to show this phi is directly an isomorphism, but I was trying to give you a map from P2 to a rational map from P2 to P1 such that the P1 followed by P2 becomes identity. Yeah. So this map is okay, I think. Um, so if I take wait a second. So if I take so what time is it? Yeah, so we have gone way over time. But okay, so maybe I'll work this out, and you can and try to put it on notes. So uh, let's just verify this. Yeah. So um, uh, yeah. So let me try to work out. So I thought we could write a map in the reverse direction as well and get this isomorphism. Okay. So let me work this out and put it in the notes. Yeah. And yeah, so maybe next time we will talk about um, Bezo's theorem. Okay, so writing down examples explicitly in projective thing is a bit complicated with all this homogeneous and stuff. So let me stop here.